Cool. All right, morning. So last week we looked at some Arduino and electronic stuff. Today we're just going to finish off our look at electronics, in particular looking at some of the components you guys might want to use and the sort of stuff you're doing. It's going to be sort of quite a high level look at it, just sort of explaining what these things are, how they work and how you use them. But yeah, it's up to you whether you find whether they're going to be useful to you or not. So we'll start off with some of the common components. These are things you're fairly likely to come across either doing your own stuff or, hold on, I might actually just duplicate that because I can't see what I'm doing. Yeah. There we go. That's still not particularly useful. Yeah, so these are common components you're fairly likely to come across. I'll put this lecture material online. There's actually a couple of links down the bottom once that thing finally disappears, which I've found and used before and found to be quite helpful. So just close some of these ones. So there's this DC Lab one, which is kind of the, I guess, the Fisher-Price style electronics thing. So it's pretty simple, like graphics and stuff. I've just found out as of this morning that you now need to sign up for an account to use most of the things, but it looks like the accounts are free, so it's not such a big deal. But you know, you basically go on here and you've got like your proto board, and you just dump some components onto it, and then you can connect them up with wires, and then you can see stuff happen. So yeah, if you try and use so there, obviously a switch is a component we can use. How do I get rid of this wire? Get off there. So yeah, you can sort of wire up basic things. I think you can actually check on, yeah, so you can check what sort of amps are running through them and stuff like that as well. So you can get a rough idea. As I said, like if you try and use other things, it asks you to sign up for an account, which it appears to be free, but I've signed up for an account, but I'm still waiting for them to email me back to let me know whether it is actually free or not. But yeah, so there's one, sort of simple and pretty way of doing it. The other one, which we're going to probably be using more, at least in these lectures, is this IndiaBix one. So this basically is slightly less pretty, so it doesn't have nice pictures of stuff, but it actually sort of shows it's more like circuit diagrams and shows a lot of information. This is something you may need to, because it runs on Java, so you may need to go into your Java settings again and add it to your security panel, so edit site list and add IndiaBix in order for it to actually run them. But yeah, once you run them, no, I need to update Java. You'll see something like this. So you can see here's a 5-volt power source. We've got a couple of resistors and a couple of grounds, and you can see the way current's flowing through it. And when you mouse over various parts, you can see the component name and some information about them. So, here's a wire, and there's 55 milliamps of current going through it, and 5 volts going through it. And then down here, so we're going 55 to 5, and the other side will be 5 milliamps. And then power is going through the resistor, so the 50 milliamps going through the resistor, 5 volts differential, so there's 5 volts here and 0 volts here. The resistor is 100 ohms and it's using 250 milliwatts of power, and so on and so forth. And you can do stuff like decrease and increase simulation speed, the speed that things are running at, so we can really slow it down, sort of see, so the dots indicate basically the amount of current which is passing through it, so you can see a lot more currents passing through this way than this way. And you can increase and decrease voltage to see what happens. You can also right-click on it and add things like wires, resistors, passive components. All the components you might want to work with, you can add by clicking right. But what we're going to be looking at is, they have basically a huge amount of like sort of example circuits, I guess, which sort of show various components and how you can build stuff out of them. So keep your Java up to date. Yeah, so you can basically look at various components. You start off with seeing how a diode works, and then this must be a way swap that around maybe. If I just go add wire. Oop. So perhaps not the easiest interface to use, but there we go. So now if we swap the wires around, you see current's no longer flowing because now it's trying to flow backwards through it. But yeah, you start off with sort of simple things in these examples, and then they build up from, you know, just using a standard diode, doing half-wave rectifiers, full-wave rectifiers, and all sorts of stuff, how you can do, start building radios and stuff. So there's quite a few good examples in here, but we're going to look at them later on anyway. But yeah, to begin with, some of the common components we're going to look at: power sources, switches and buttons, resistors, potentiometers, diodes, lamps, LEDs, capacitors, transistors, and relays. So basically, these are the sort of stuff which come in your SparkFun Arduino kits that you're likely to be playing with, and you know, some of these you probably already know about, but we'll go through them anyway. So starting with power sources. So here's a range of sort of batteries and stuff down the side here, from right up the 4.5 volt. I don't even know what the name of the style of battery is, but then down to your 1.5 DC, AA, AAA batteries, and then, you know, other batteries beyond that sort of. So there's a whole range of batteries depending on what your project calls for. You've got like some things you might want to consider as the physical size. So obviously some of these batteries are larger than others, some are smaller. Typically the size is related to the voltage and the amount of power it can produce over its lifetime. Yeah, so it's capacity. So voltage, capacity, and current is something you need to consider. So obviously you might need a certain amount of voltage. If you're running an Arduino, you're going to need to provide it with at least 5 volts of power, otherwise it won't do anything. So, you know, if these ones are providing 1.5 volts, you're going to need multiple of them to get it to go, and so on and so forth. And we'll have a look in a second about how we can increase the voltage or current or whatever by placing our batteries in parallel series. So depending on what sort of applications you're looking at, you might want to consider the lifetime and self-discharge. So batteries will go flat over time, even if they're not connected to it doing anything, not connected to anything, not doing anything, because of the chemical reactions which are happening in them. So if you're wanting to build something which is going to last over a long time, those are obviously things you want to consider. Whether you're going to use primary or disposable batteries, so alkaline batteries which you throw out, or rechargeable secondary batteries. And the chemical composition might be something that you're interested in as well if you're an environmentalist, like whether you want to do alkaline or lead acid. Well, alkaline batteries aren't rechargeable. Lead acid, nickel metal hydrate, nickel cadmium, and lithium ion batteries are generally rechargeable. But you know, the further you go across this way, the more complicated it gets to charge these things. And particularly for things like lithium ion, if you charge them incorrectly, they will explode or catch on fire, which is generally not a desirable trait in your electronics. And this is the sort of symbol for a power supply. Sometimes it'll just be the 2 lines, like one large, one small. Sometimes it'll have multiple. Technically, if it's just one large, one small, it's one cell, and like this is a power supply or battery, but it's pretty arbitrary, really. So let's say you want to be able to power your Arduino, but you've only got AA batteries or whatever, C batteries. You can actually increase the voltage by basically connecting all the batteries in series. So when your batteries are connected in series format, or the voltage is increased, the current in the circuit will pass through all batteries as they're connected in series. So the current remains the same, but the voltage increases. And by connecting the batteries in series, you increase the total voltage. A higher voltage means the component device will have a stronger output, e.g. a light will be brighter. So the current through our circuit here in our series circuit with voltage, so the total value of I, or the total current, is equal to I1, is equal to I2, is equal to I3. So the total current in the circuit is the same as the current out of here, the current out of here, and the current out of here. However, the voltage is equal to the voltage of this one, plus the voltage of this one, plus the voltage of that one. And this makes it pretty obvious. We have 3 12-volt 1 amp batteries, and we connect them all in series. So connect the positive of one to the negative of the next one. And then at our load, we're going to have 36 volts over it, but still only 1 amp. So these remain the same, but the other ones get added. So we can get a total output of 36 watts out of this. So what if you want to increase current? So what we can do is, if we need to increase the current of the batteries, we can connect them in parallel. Total voltage remains the same when it's in parallel, but the current is added together. So if we look at this example here, we have them all connected positive to negative. Here we have all the positives connected together and all the negatives connected together, and then the load is driven off that. And the same battery is 12 volt, 1 amp. So now at the load we still have 12 volts, but we have 3 amps running through it now. And if you want to increase both of them, you just build a circuit which has both parallel and serial battery connections in it, and that battery is the wrong way around, which I've only just noticed, but that should be facing the other way. So yeah, this will basically increase the voltage of these two will be added together, and then the currents of these ones will be added together, and then the voltages of these ones will be added together. So you could imagine if you had those 12 volt batteries before and you wanted to get so you had 12 volt and 1 amp and you wanted to get 24 volts and 2 amps, you might connect them a lamp or whatever else. You might connect them like that. So this is 12 volt, 1 amp, 12 volt, 1 amp. So effectively the overall value of this is now 12 volt, 2 amps, and the same thing here. So the overall voltage and current coming out of the two of these will be 24 volts and 2 amps. So you can basically build up power supplies out of batteries like that. With this sort of example here, I mean, you've got batteries connected in parallel and series and just generally a big shambles, so I'd highly avoid trying to replicate this, especially considering one of the batteries is in backwards, so this isn't actually going to do anything. But yeah, perhaps not the best example to show, but you sort of get an idea, you know, that you can connect these batteries up to change the voltage and power, voltage and current if you need be. So what if you don't want to use batteries, because batteries are generally more trouble than they're worth unless you're really concerned about portability? You can obviously plug stuff into the mains power. So straight out of the mains, you're going to get 230 volts and 50 hertz in New Zealand, at least. If you're over in the States, you're going to get like 110 to 120 at 60 hertz. You know, so these are things you need to consider if you want to make a worldwide power source. But generally speaking, very few things run directly on, or very few of the electronics that we run into most of the time run directly on mains power. They run on regulated DC power. So basically, you convert your mains power into DC, your mains alternating current into direct current, and then process that. And we'll look at how you can actually do that in a minute, sort of. So I mean, you guys know the difference between direct current and alternating current. So direct current is basically always positive and ideally stays at the same voltage. If you're running off a battery, that voltage will probably decrease over time as the battery wears out. Whereas alternating current goes from 0 up to its max, and then back to 0, and then to negative max, and so on. So it's like a sine wave versus a straight line, really. So this is typically, if you look at a diagram, this is what your alternating current source will look like in your diagram. So it's like that waveform there. Whereas if you're looking at regulated DC power, typically they'll say something like VCC or plus 5 volts or something like that, and you might see them diagrammed like this. So either an arrow pointing towards it or a sort of a T shape which connects up. And then that will need to go into some sort of low voltage potential. So this is high voltage potential, and then the low voltage potential is commonly referred to as earth or whatever, regardless of whether it's alternating current or DC power. And you might see these sort of symbols. This is typically the most common one here, at least in my experience, but there are other symbols. I don't know why they haven't just standardized and picked one, but people use different designs. So if you see these, this is basically what it means. It's the other end. So this is the positive voltage, and this is the 0 voltage or whatever else. And obviously there are other methods you can use. You can use things like solar. So you can plug in a solar panel, and various solar panels will output various voltages and currents. And even beyond that, it'll depend on the amount of light which is available and stuff like that. So often you'll find 5 volt solar panels, so if you want to charge your cell phone or whatever, or you can find 12 volt solar panels for charging cars or whatever else. And the amount of current they will produce is typically relative to the amount of sun. You have a dynamo, like if you're on your bicycle and you've got a little thing which turns around, or in vehicles they have an alternator which does a similar job to the dynamo, so it converts mechanical energy, so rotating energy into into power, so it's basically the opposite of a motor. Or you can plug in a lemon or a battery if you really are so inclined to get some voltage out of that, but they're not particularly great power sources, but you know, they're there if you need them. Yeah, so that's powering your circuit. Then if you want to have some user input, that's usually a good idea, because most of the time you don't just want to plug a light into a battery and leave it. You want to have some way of controlling it. So you can have switches or buttons. So they are mechanical devices which connect and break electrical circuits. And typically speaking, switches and buttons make and break a physical connection. So they actually connect two pieces of wire together and then disconnect two pieces of wire. So it's actually physically making and breaking the circuit. So they have two states. They can be open, which means they're on. Closed, which means they're on, or open, which means they're off. So when they're open, you know, the two pieces of wire are actually physically separated. When they're closed, the two pieces of wire are touching. And if you get the switches you guys have in your Arduino or your SparkFun kits and break them open, you'll actually see like the push button switches usually have the plastic button, and then it's got like a little piece of metal like that, and then a spring, and when you push down, that piece of metal just closes to the legs of the switch. If it's a sliding switch, often it's just a piece of metal which slides back and forward, so it makes that connection. So switches are typically like sort of, you set them on or you set them off. So this is the difference between a switch and a button, because they do mean different things. So a switch you turn on and it stays on. You switch it off, it turns off. Button, you have to push it and hold it in for it to be off, or to be on, and then you let go and it releases, or vice versa. It's either normally on or normally off. These are switches. Well, actually over here, this is a switch here when you draw in a diagram. So you can see when you flick that will connect to those two parts and stay on. This is a button, so the idea is you push this in, it stays on, and then it'll pop out. And depending on whether it's normally open or normally closed, you'll draw it like this. So this is a normally open switch, so unless somebody's pushing it, this will stay off. And a normally closed one, a normally closed one looks like that. So basically the same thing, except this one's open, this one's touching, and when you push the button, it'll disconnect it. So, I mean, it depends, like, you know, for example, like kill switches are often normally closed buttons that you push them and they disconnect the power. Although, yeah, they're usually switches rather than buttons, but, you know, you can imagine if you have something you want to be able to, you want it normally running, but you want to be able to stop it, you'd have a normally closed button. You can also have single or double pole or single or double throw switches. So double pole switches are equivalent to two single pole switches. So that is a useless eraser. So a double pole switch is drawn like this, and often with a line through it, like this one up here. And it basically means you have one button which switches two switches. So, trying to think of an example here. Say you want, in your bathroom, you know, you have a switch which turns on the light and the extractor fan, because it assumes if you're going into the bathroom, you're going to have a shower. So you might have something like this, which has, you know, two separate things which go from your AC connection, and one goes to the light in your bathroom, and the other one goes to the fan, so some sort of motor. And it has one switch which basically throws two things. This way, even if one of these burns out or something, so the light bulb burns out, the motor will keep running, because it's actually a separate physical connection rather than sort of running through in series or whatever else. And the other one you can have, so that's a double pole switch, and a double throw switch is usually the more interesting of the two, and probably the more useful as well. So a double throw switch looks like this. One there and one there. Yep, so this is the one on the right here. And this basically means the switch can connect one of two different circuits. So you could imagine you might have a light, like a traffic light sort of scenario, where you have a green one here and a red one here. And when you switch to the green one, it turns or sorry, when you switch one way, it turns the green light on. When you switch the other way, it turns the red light on. And typically, like most of the light switches in your house are often these double throw. Well, if you've got multiple light switches which control a single light, often they use these double pole things, so that when you switch, as long as both switches are in one way or the other, the light will turn on. Otherwise, yeah, it won't. So yeah, those are the two differences. So double pole here and double throw. Double throw allows you to control two circuits, like it's either this one or this one, and a double pole is just two switches which are wired together internally, basically. Moving on to resistors. So we talked about these a little bit yesterday, but they're typically drawn one of two ways. So this is a resistor and this is a resistor. Well, this one's generally more commonly used, but you'll see both of them. And resistors resist the flow of electricity in a circuit, so that's where they get their name from. And Ohm's law, so this time I've got it correctly in the slides, and in fact I updated the slides before I uploaded them. Thanks for people who noticed that. Actually, I forgot to say as well, the easiest way, well, when I was doing electronics back in high school, the way we learnt it is if you put it in a table like this, V on the top and then I and R, you can basically figure out everything, or the relationship between things, just by covering up whatever you're trying to find. So if we're trying to find V, cover up V and it's I times R. If we're trying to find I, it's V over R. And if we're trying to find R, it's if we're trying to find R, it's V over I. So that allows you, obviously, that's just rearranging the formula, but if you put it in a pyramid, you don't have to figure out any of the math, you can just look at it. So resistors, the ones you guys have got in your SparkFun bags, have a little label on the front which says what sort of voltage or what sort of resistance they have, which makes it easy, but they also come with color codes which tells you what the resistance is. So you'll see on one end there's a stripe which is sort of separated from the others, so these are all sort of, you can see, close together, and this one's sort of away on its own. So this is the tolerance, and the other ones are the resistor value. So you start reading from this end, and we basically say, okay, what's the first color? Is orange, so it's 3. Let me write this down. So if we start reading, so we look at this one, it's 3. And then we look at the second one, and that's 3. And then the third color, or if it's got 4 bands, the last color anyway, tells us how many zeros we have at the end, and brown is 10, or so 330 ohms. So we look at the first one and we say, okay, that is 3, the second one's 3, and then we times that by whatever's in that last one. So if it was orange, black, it would just be 33 ohms. This is 330 ohms. This would be 3,300 ohms. This would be 330,000 ohms, and so on and so forth. Anyway, so you can look at these color bands. There are various ways to remember the order of these. I'll leave you to look it up and find out your own ones, like little pneumatic devices. I just go on the web every time and look it up, because every time I try and remember one of these, mnemonic devices, I forget. So here's an example here, which was obviously accidentally left here by me last time. And looking from one end to the other, we have brown, black, and red. So brown is 1, black is 0, and red is 0, 0. So this is obviously a 1,000 ohm. 1 kilo ohm. 10 kilo ohm, sorry. Is that right? Brown, red. No, sorry, it is. 1 kilo ohm, sorry. That's right the first time. Yeah, so this is 1 kilo ohm. So 1 and 0, and then 2 more zeros from the red. So, 10 times 100. And yeah, so that's, you can have a look at that. And so I said, we have one more band at the end, which is this band here, which defines the tolerance. So if you remember when we looked at it on the, plugged it into the multimeter last week and had a look at it, we had, it wasn't, the 330 ohm one wasn't 330 ohms, it was like 325. The tolerance is basically how close to that stated resistance it is. So if we open up calc, and we say, so that was a 1 kilo ohm resistor, and the last band was gold, means that it can be anywhere between 950 ohms and 1000 times 1.05, 10,050. So it'll be somewhere between 950 and 1,050 if we measure that. And I didn't bring the multimeter with me, but you're welcome to take it away if you want and test it. It should be between those two values though. And you can, typically the ones you'll see are gold and silver. Gold is fairly common. Silver is if you're buying really cheap components. You can go all the way, like after that you may see brown and red, but certainly you don't see them very often, which are down to 1 and 2%. And if you're buying really, really expensive components, you might even see them go as far as violet, which is 0.01%. So if you're doing really, you're building circuits which need really sort of reliable values, you might see down here, you know, if you're trying to build your own multimeter or something, you might want components like this because you want to reduce the error as much as possible. For the sort of things, if you're plugging a light bulb in, the difference between +5 and +0.1% in the brightness of the LED is going to be completely imperceptible, so it doesn't really matter. Yeah, so that's how you read a resistor. Then how we change the value of them. So series versus parallel. In series, the current across all of them is the same, but the voltage is proportional to the resistance. So so if we have our power source, what was it drawn there? 5 volts. Power source, and then we have 1 resistor and 2 resistor, and then ground. The current will be the same. So let's say this is a 5 volt 1 amp. That means there'll be 1 amp across here, or running through here, and 1 amp across here. Actually, let's give these values. So let's say this is what's going to be a nice one. Let's say this is 1 kilo ohm, and this is also 1 kilo ohm. So both of these will have the same amount of current through them. So remembering the train carrying coal analogy, the train's got to run through both of these. It's not ditching any of its things. But each of them will be burning half of, well, the proportional amount of voltage. So this is a 1 to 1 because it's 1 kilo ohm to 1 kilo ohm. So this will get use half of the voltage, and this will also use half of the voltage. If this one was then, I'm trying to think of a way to do this. Maybe a 5, so this is now 5 kilo ohm. This will be a 1 to 5. Is that going to work? Maybe 1 to 4. So this is 4 kilo ohm now. So this one will use 1 volt, and this one will use 4 volts. So this one's going to burn or use more power than this one, use more voltage than this one because it is 4 times more resistant. And we can see some examples of that actually if we go back to that India Bix website. Whoops, where are we? Somewhere, resistors. This is a nice little example here which allows us to, which allows us to connect various resistors up. It's not particularly useful, is it? Because they don't have, let me just change the value of this to 100 ohms. And what's that? That's 5 volts. So this is a nice wee example because we can actually connect resistors either in series or parallel or whatever else. So you see here we have a 5 volt source which is delivering 26.5 milliamps plus or minus. And if these are the same, 100 ohms and 100 ohms, we would expect to see the voltage across them be more or less the same, but they're not for some reason. But it's close-ish anyway. 100 ohms, 100 ohms, 55, 70. Anyway, these should be the same. I'm not sure why in this simulation it's not. But yeah, we should be seeing the same amount of voltage pass through the top one as the bottom one. If we then do these ones here, we would expect this to be using twice as much voltage as this one, so 1.5, 1.6 versus 3 point something. I'm not quite sure why the voltage isn't the same in here, but yeah, this one, the current through them all should be the same anyway, 17.3, 15.3, brilliant. So they should be the same anyway, and the voltage will be twice as much in this one as this one, because this is offering twice the resistance as the other one. And then you can do various things. Oh, that's actually probably why there. That one was open. So let's go back. Yeah, okay, so sorry, I actually had that one closed as well. So there was a third resistor in the mix that I didn't notice. So now we see we've got our 5 volt as voltage source and 25 milliamps coming out of that. We have 25 milliamps on this one and 25, well, going through this one, 25 milliamps going through that one, and 2.5 volts here and 2.5 volts here. So we have the same amount of voltage and the same amount of current going through both of these. If we hook this up, we'll have the same amount of current, so 16.67 milliamps traveling through the both of them. But this one now has 3.33 volts and this one has 1.67 volts. So this one has twice as much voltage going through as this one because it's twice as resistive. And just quickly go back to this one. So that's in series. In parallel, the voltage across all is the same, but the currents are added. So if we now open this one and close this, so you'll see here we have, so if they're running in parallel, so we have one voltage can go through this way and voltage can go through this way. The voltage is the same through both of them, so there's 5 volts across this one, there's 5 volts across this one, and the current is added. So this is 62.5, this one is 50, and this is 12.5. And the values across these will be proportional to their current as well. So if I change this to 100 ohms, we would expect to see 50 milliamps through this one and 50 milliamps through this one because they're the same 100 milliamps in total. And if we change this to 200, we've got 50 here, we've got 25 there. So the current is proportional to the ratio between them. So everyone sort of follow that. The voltage is proportional to the resistance in series, and the current is the same, but in parallel it's the opposite way around. The voltage is the same, but the current is proportional. Everyone happy with that? Yep, cool. Right, so that is these resistors, and then we have potentiometers. So we looked at the potentiometer. Looked at a potentiometer before when we looked at the Arduino, the little twisty, turny knob thing, like this one down here. And basically, this is just a resistor, but you actually can change where the current comes out of, or how far you're measuring across it, basically. And they're typically drawn like this, so a resistor as before, but it's got a little arrow pointing to it. Or a resistor like this, with same as this, but with an arrow pointing to it, which suggests that we can actually change the voltage amount. And you'll often see these either as rotary potentiometers, like the ones you guys have got in your Arduino kits where you twist them, or you can have linear ones where you just slide the thing back and forth and it measures the resistance like that. And your potentiometers will often have some sort of rating which says what their max, or how the resistance works between them. Right. Diodes. Diodes only they're a semiconductor which only allows voltage to go in one direction. So power can go from the positive to the negative, but it can't go from the negative to the positive. So the stripe always goes towards the negative side, and this is what a diode actually looks like, and this is what it looks like in the circuit diagram. So you notice both the diode, the physical diode, and the circuit diagram has this line or stripe here, and that always goes towards negative. So you can actually use them for rectification. So I talked before about if we have 230 volts, we might want to convert that into something else we can use, and we can actually use diodes to create basically convert it from 230 volts AC into something in the DC using what's known as rectification. So if we have our power source here, our alternating current power source, and then we go into a diode, and then we have some sort of load, and then we go to earth. So if we don't have that diode to begin with, We go here, the voltage over the load. We look over here. Will look something like this. So it'll go from 0 up to the maximum AC voltage, down to the minimum AC voltage, and so on. It'll keep repeating that pattern. If we then throw a diode in here like this, what will happen is diodes only allow current to flow one way. So essentially everything underneath that gets wiped out. So you can see now we're just going to have this repeating pattern like this, where our power is always positive. So the load is only, say this is a motor or something, instead of the motor spinning one way and then spinning back the other way as the voltage goes negative and positive, negative, positive, now the motor is only going to ever turn one way, so it's only ever going to say move in that direction, rather than before where it would go that way in one direction, sorry, that way with the voltage going positive and that way going negative. But you can see here we've got all these big gaps, so what we can do is build what's known as a full wave rectifier. So this is a half wave rectifier because we're only dealing with half of the original wave form we have. And then we can build a full wave rectifier, which looks like this thing in the bottom here. So we have diodes, oops. And then they go that way too. And we put power into this one. And dropped off the bottom half of this diagram. Let's have a look. So they come, the voltage comes from there and then goes into there, and then this would go back into our AC source. And what happens now is if voltage is coming out in this direction essentially, so this is, if we imagine that our AC pattern, basically if it's positive it's coming out in this direction, or the current is moving in this direction anyway, and if it's negative it's moving in this direction, or this could be connected to ground, whatever, because it's going to just reverse direction anyway. When this is negative, current's going to flow the opposite way. So if it's coming one way, it'll go through here, back into here and back out to ground. So following I have a red pen somewhere. If it's, say, this top half of the wave here, it's going to come up here, then down this way, through our load, back up here, down there, and out. So the power is going from this way through our motor, and then if I had another pen that would be really useful, but I don't. If it's going the other way, so it's coming from the ground or from here now, so now we're looking at this part of the wave, it'll come from here and it'll go out here, up this way through the motor in that direction, down this way, and then it'll come up here and back in this way. And yeah, so this is the path it takes in the other way. But you can see both times, regardless of which part of the wave we're looking at, power is passing through the motor in this direction. And what we actually end up getting from a motor now, so if you remember when we had our half wave rectifier, it looked like this. What we end up with now is what's going through the motor looks like this. So here we've basically clipped off and lost half of the wave. So this is a half wave rectifier. This is a full wave rectifier. So what it's essentially doing is just negating or inversing the negative part of the wave, so it's now positive the whole way through. This is a little bit advanced and not something you guys are going to have to know what it is or how to work, but it sort of shows you what you can do with diodes, because you might be wondering why would you ever need a diode. You know what way the current's traveling. Well, you can actually basically convert from AC into a sort of DC, or the beginning stages of a DC anyway, using this. And if we jump back to here and open up diodes, we can see so this is our half wave rectifier here. So you see this is our AC power source when that loads. This is our AC power source, and if you watch actually let's just move that out of the way to begin with. If you watch the direction these dots are moving, So they go clockwise, and then they go anti-clockwise, and then clockwise. And you can sort of see this is what's coming out of the source here, and this is what's going into the load. So now if I delete this, whoops, if I can. Delete. Go away. And now put this back in. You'll see this is our half-wave rectifier now. So only when the voltage is positive is it going to go through. So it goes positive, and then it tries to get back through the diode, but the diode won't let it go back through. So this is the half-wave rectifier we saw before. Like that.
What's causing it to not quite go as high on the voltage? Is it the voltage on the y-axis?
You mean why is it like slightly lower here than it is here? So the diode itself will use up a little bit of power. Yeah, but I mean it's not a huge amount, not a substantial amount anyway. And there's various other things which I'm not going to cover, like activation voltages and stuff. So diodes need a certain amount of voltage in order to let anything through. I think it's 1.3 volts or something in order, but that depends on the diode you get. And you can get Zener diodes, you can get signal diodes and all that sort of stuff. But yeah, so there will be a slight amount of power used by the diode. Every component, even the wires, in this one they don't actually have any resistance, but in reality, like a wire like this will have a slight amount of resistance. But you know, we're only talking theoretically here. So, so yeah, that's the half-wave rectifier. And then if we look at our full-wave rectifier now, you can see, I might just see if I can slow this down, maybe not quite that much. So you can see the path it takes when it's when the AC current's going in one direction, it goes through this diode, through the load, and back out of this diode. And when it's going the other direction in the red, it goes through this into the load, and then through this back to the source. And now if we look at our things, our half wave, we have this gap where the other half of the wave was. Our full wave, we have the wave going the whole time, and this little gap in here is basically the same thing. We're talking about the activation voltage. It needs to be over a certain amount, so when it's not at that amount, no current will flow through. Right, so that's just a little aside on what you can use diodes for. So half wave or full wave rectification. Obviously you can use it for other things as well, so oftentimes they're used, and I can almost guarantee there's probably one in the Arduino connected to the power source, so that way if you plug a 9-volt battery in the wrong way, or if you have one of those DC things that you can change the plugs on, so if you plug it in the wrong way around, it won't fry your circuit. It'll basically make sure that you have to have the battery or your power supply plugged in the right way, so it won't fry your Arduino. Although obviously diodes, like everything else, have their limits. If you try and push too much voltage through them in the wrong direction, they will eventually burn out, and then they either won't conduct electricity in either direction, or arguably worse, they will actually basically function like a wire and let voltage through in either direction. So yeah, they work within their operating threshold, but if you push them too far, if you got one of the diodes in your kits and connect it up backwards in a car battery, it would just fry it, and then if you're lucky, it'll just basically burn out internally and stop working. If you're unlucky, it'll basically start acting like a wire and then probably catch on fire pretty quickly. Right, so moving from there into lamps and light emitting diodes. So you have lamps, which are typically drawn like this, so a circle with a sort of bump in it, or the way I tend to draw is a circle with a cross through it. So this is a lamp like in your traditional home lights, like your screw-in lights. So basically power goes through, and then you have like a very sort of thin, low resistance wire in the middle, which gets really, or heats up and gets really bright. So it's basically sort of almost like a short circuit sort of thing. It's lighting up, but you fill it with an inert gas so that it doesn't burn out quickly. So they allow omnidirectional current. So current, you can wire in a bulb either direction. So you could put 5 volts here and ground here, or ground here or 5 volts here. It can connect up to AC, and it'll flow through both directions, one after the other, and it works just fine. It'll light up and whatever else. However, they're very fragile, so, you know, if you've ever sort of, especially when they're warm, if you've ever like tapped or bumped a light bulb when it's warm, they tend to blow out the filament pretty quickly, and they're extremely energy inefficient. So, I mean, you've only got to try and touch a 60-watt bulb, and absolutely fry your hand to realize that most of the energy you're trying to turn into light is actually being turned into heat, and this is why everyone's like typical bulbs these days. Everyone's talking about energy efficient bulbs. The other thing you can have is LEDs. So LED is light emitting diode, and it basically is a diode exactly like we saw before, except in addition to letting current only flow through one direction, it lights up. So the diagram for an LED looks like this. So you have the LED thing as before, however you have a couple of lines going out of it this time. Sometimes these have a circle drawn around them as well. So it only allows unidirectional current, so the current will only flow through one direction. This is why you can't get an LED bulb and just stick it in your original light socket, because your original light socket is AC, whereas LED is a DC, so you have to get a transformer to drive your LED bulbs, or if you get one which does screw in, it'll have the transformer built into it. They're quite robust, so they don't blow out anywhere near as often as lamps. So often your typical incandescent bulb will burn out after a year or two in your home, whereas LEDs, they say they've got a lifetime of 10, 15 years. They're more energy efficient, so they do heat up, but nowhere near as bad as lamps do. However, they're more susceptible to current and heat as well, so they need a more controlled power supply, a cleaner power signal coming through in order to work. And when I say heat, this is actually kind of a cool thing which you can do. So LED in liquid. So if you get your LED and you cool it right down using liquid nitrogen, what actually happens? This is obviously quite an extreme example. So this is an orange LED. Here you can see it's just connected up to positive and negative, and then you drop it into liquid nitrogen, and as it cools down, you'll notice the color of it starts to change. So it goes from orange to a yellow, and then eventually to a sort of a greeny color. So they're more susceptible, and because LEDs do actually produce heat themselves, they will often change colors as they warm up compared to their normal color as well. So a bulb will, like a typical incandescent bulb, will tend to stay the same color regardless of its temperature, more or less, whereas LEDs will change color depending on their temperature and how much current and everything goes through it, and they need a certain amount of current to start glowing, and so on and so forth. With the LEDs you guys have in your kits, you usually want to put them in series with a resistor to avoid the LED blowing, so they will blow if you put too much voltage through them. So typically you'll use like a 330 ohm resistor or something. If you have 5 volts going into it, you put your bulb or your LED and then a 330 ohm, what's known as a current limiting resistor, which will stop it from getting too much current through it and blowing. And you can buy many different colors available, and even RGB LEDs. So there's white, blue, whatever. Typically, you see red, yellow, and green. Blue ones tend to be a little bit more expensive because of the material which is needed in them, and white is often the same. Or you can buy these RGB LEDs as well, which often have one ground leg, and then you have a separate leg for the red, green, and blue color, and then depending on the amount of voltage you can change or lower the brightness, and then effectively like a pixel on a screen, if you turn the red, green, and blue on all the way, it'll be white, and then various levels will change the color of the LED, or the perceived color anyway. So like diodes, they only allow current through one way. On diodes, you have the stripe which goes towards negative, and on LEDs you have, so you can sort of see it on this one here, you have one side of the LED, so often you have the round sort of dome LED, and then it'll have like a little lip below it. The lip will be cut off on one side on the LED, and that is the negative terminal, or often, unless you've snipped the legs off yourself, one of the legs will be longer, the shorter of the two legs will be the negative one as well. So yeah, basically the round edge goes towards positive, the flat edge goes towards negative. And various other things have various other ways. So obviously some of these ones which are square don't have that, but if you look at the legs before you cut them off, the shorter one will be the negative terminal. And then I think we've got just a few more of these basic components that you're likely to look into. Capacitors, so will typically either be drawn like this or one of these two things. And capacitors basically store an electric charge as potential difference. So a capacitor has what's known as two plates inside it. So two plates with an electrolytic compound in the middle. So what happens is you put voltage in, and one plate will start charging up with electrons and the other plate won't. And then when you take that voltage off, if you have a connection from one side to the other, it will balance out again. And this was a sort of a nice little diagram which uses, fluid with a rubber membrane to sort of illustrate how a capacitor works, or a metaphor for how a capacitor works. So if you imagine this is a tube here with a piece of rubber which can flex, as you start to charge up one side of the capacitor, it's the equivalent of putting pressure on this membrane. So the membrane will flex out. So this is now at a higher pressure than this is. And then when you release that pressure, if it can, it'll attempt to balance this out. So the fluid will flow back around until it reaches a state of equilibrium. So you can actually use capacitors kind of like a little mini battery. You charge up one side, and then voltage will flow through to the other. And the amount of charge is stored. The amount of charge stored is known as a capacitance, and it's measured in farads. Often you will be talking in the sort of circuits you guys are often working with microfarads. So a farad is actually quite a large amount of charge stored. If you have a one charge capacitor and you grab either end of it, you will feel it. If you're lucky, you'll only feel it. If you're unlucky, you'll kill yourself. So, but I mean, we're talking about like farads are, big capacitors like the size of your hand. Even the ones, so let's see if we can find a picture of a, trying to find, oh, here we go. So this is 1.5 farads here. So you're going to probably know if you're wiring one of these into your Arduino, because you'll be like, why the hell is this thing so big? But yeah, so we're often sort of talking about microfarads, or at the very most millifarads. And yeah, basically you charge them up, you store current in them, and then you can release that current. So you do some cool things with them. You can do timing circuits, because if you know how much capacity your capacitor can hold, and you know how much energy is discharged, you can actually time something. So you fill it up, and then it'll discharge over time. So you can use it for timing circuits. You can use it for energy storage. So there's obviously the race is on at the moment. Everyone's trying to do these supercapacitors, which can hold, because the problem with capacitors is they don't generally hold a huge amount of power, and they discharge very quickly. But everyone's trying to do these supercapacitors at the moment, which will basically replace batteries. The main advantage behind a capacitor compared to the battery is that you can charge it in seconds. So you get your car battery, or like you look at these electric cars like the Teslas and the Nissan Volts or Leafs or whatever else, and you need to plug them in overnight to charge them. Once these supercapacitors become affordable and a reality, you can basically stop off at someone's house, plug in your car for 15 seconds, and it'll be charged. Or, obviously you go to a petrol station, you're driving cross country, you don't want to have to plug in your car for 12 hours at the petrol station. These supercapacitors will allow you to plug in your car for like 15 seconds, and you'll charge it up the full thing. So everyone's trying to do these things, so they'll be great when they come along, but it's taking its time to get there. The other thing they can do, which batteries can't do, is capacitors can discharge extremely quickly. Batteries, they can only let their energy out in a certain amount because of the chemical reactions which need to happen, whereas capacitors, because you basically have this huge energy potential difference in here, they can discharge very quickly, which is really useful if you want to build a laser, you want to conduct nuclear fusion, build a particle accelerator like the Large Hadron Collider, or build a railgun. So you see plenty of examples of people, well, not plenty of examples, but people building railguns, homemade railgun, and you'll often see people basically get a ton of capacitors, and then they charge these capacitors up and discharge them very quickly. It's running very slowly. So there you go. This guy's. He's using three 220 microfarad, so three 2.2 millifarad capacitors. So even these are quite large, and then he's adding them up, and you charge them up, and then you discharge them at an instant, and it accelerates using magnetic force, a projectile at extremely fast speeds. So you can see here, when he discharges it, it's happening. There's so much power going through there. There's actually a huge spark. Yeah, and the US military has just, I think, actually got their first aircraft carrier with a railgun on it, and it has huge, huge, huge capacitors in there. Anyway, another thing you can do with capacitors is they operate in sort of the opposite direction, or the opposite of a diode. So a diode only allows direct current to pass through it, so current in one direction. You can actually use capacitors to block direct current. So what happens is, if you try and push direct current in it, so current's only going one direction, it'll go through, but eventually you'll reach the maximum capacity, so this membrane won't be able to stretch any further. So, you know, you plug your 9-volt battery into a capacitor, and it'll allow electric current through until it sort of flexes out, and then it stops. It's reached its maximum potential it'll let, and then it won't let any more current pass through, and it'll just stop. Whereas if you have alternating current, essentially the membrane will be flexing a little bit in one direction than the other, and you can actually, block direct current but allow alternating current. And the last thing which you can do with them, well, not the last thing, but one of the other things you can do with them. So we have our full wave rectifier here, and you can see we're going from 3.56 volts down to 0 volts. That might not be ideal. If this is, you imagine this is the light, it's going to get bright and then it's going to get dim. What we can actually do is we can throw a capacitor in the mix as well, and we charge up the capacitor when we get to the top of the thing, and then when it gets to the bottom we start discharging it. And so you'll see here we've got our full wave rectifier. So if we compare these two diagrams, the only difference is we've thrown a capacitor in there, and if I start this, what happens is when we get to a certain amount on the peak, so you'll see if we have this diagram here, what happens is we charge up our capacitor, and then once we get to below a certain amount, the capacitor will start to discharge and it'll start releasing its voltage out. And then when we hit the second peak off that, it'll start to charge it, and then it'll start to discharge, and then it'll charge, and then it'll discharge. And if we get the right level of capacitor to power supply in there, we can actually sort of start smoothing this out more and more until we sort of end up with something like this. And then if you look at our original DC current, DC signal that we wanted to have, which runs through like this, you can see we're actually pretty close to the DC signal. So, as I said, this is beyond what you guys need to know for this course, but this is how you create your little you can create one of these, basically doing what we've just seen with a transformer in there as well, which we'll look at in a minute. But if you use a transformer and one of these full wave rectifier circuits, you can actually build yourself one of these, which will convert from 230 volt mains power to this one's 12 volts DC. This isn't the most efficient way because you tend to lose a lot of energy and heat and everything else. You tend to use switch mode ones, but you can build your own one this way if you so choose. So that's capacitors. Capacitors are really cool. They're kind of hard to understand. I still don't fully appreciate how they work, but I sort of understand the idea behind them. So if you're interested in looking at it, there's plenty of information. In fact, I think even on this page here, it has an entire series of, spell it correctly, so capacitors in series, AC responsive capacitors, so on and so forth. So actually we'll just quickly load this one up because this looks like, so remember I said before a capacitor blocks DC current. You can see the current flows and flows and flows until the electric potential of this one is reached. So if we actually move the mouse over here, you can see VD, so the voltage difference between the two plates. It will eventually reach 5 volts, and once it reaches 5 volts, it's just going to stop letting power through. And you can see, this is the difference across it will gradually decrease, and we can see current stop flowing now. So you can use this like the opposite of a diode Well, a diode to AC current is the same as a capacitor to DC current, except it will take a little while to charge up. And now that this is all charged up, when I flick the switch, you'll see all the current will go from the capacitor around the other part of the circuit to try and get to its its negative thing. So it's basically acting like its own battery, which will just quickly charge. So I flick that, and now you can see the current's going to go all the way back through until the voltage differential across these two, so VD, reaches 0 volts. And then it's still flying a little bit, but it's really hard to see. It's moving so slowly, rather. That's going to eventually reach 0, and then I can charge it up and discharge it and charge it up and discharge it and so on and so forth. And when I do this, essentially I'm doing alternating current, really. So we're just letting current flow through from one end to the other. And that's sort of what we see in this example. So you see current's flying one way and then flying back, and the voltage we have over the capacitor is just slightly out of sync of what's coming out of the power supply anyway. So it's basically the same signal with a little bit of loss in there, but it's just slightly out of sync with it. And yeah, I won't bother going into that too much because I just want to go through one last slide, and then we'll have a short break. Yeah, one last slide. So the last sort of thing you're probably commonly going to come across is what's known as a transistor. And a bipolar transistor is the only one I'm going to look at today. But basically, transistors act as an amplifier or an electric switch for electric signals. So transistors have three legs on them. And transistors make up modern computing, basically, because, as I said, you can use them like an electric switch, and you can build up all sorts of crazy components out of them. So you have your transistor. Now let me figure out which way I want to go. Way there. I know that's the collector, base, and emitter. So there's two different ways, two different configurations. You have an NPN and a PNP transistor. So I'll look at the NPN ones because they're more common and they're sort of easy to understand. That's supposed to be an arrow there. But basically, if you imagine we have a signal, or rather a voltage, 5 volts here, and we'll say a load here because otherwise it's a pointless circuit, and we have our ground here, we have what's known as the base connection, and this is essentially a, what's the word I'm looking for here? It has infinite resistance when there's nothing going into the base. So if nothing's going into the base, this is effectively disconnected, so no voltage can charge. However, when I start putting a slight voltage into the base, so I think it's like 1.3 volts or something, I can't remember off the top of my head, but if I let 1.3 volts on through this, it'll allow voltage to pass through. So it's like a switch, but it's not a mechanical switch, where, like we saw before, where we actually have a physical break in it. This is actually working by, I'm not even going to pretend to understand the chemistry behind it, but you basically have this electrolytic, and when you put current into it, it'll allow a voltage into one part of it, it'll allow current to flow through the other part. But yeah, so this is a mechanical switch which physically breaks it. Here it's actually a chemical reaction which stops the voltage from passing through here unless the voltage is coming here. What's interesting about transistors though, well, other than the fact that they are a chemical or electrical switch, so you know, we can, if we want to turn this on, we can send a 0 here or a 1 here, will allow current to flow. The current which flows between these two things is a much larger amplified signal of this. So with your old school transistor radios, you cool kids are hanging out with all the time these days, basically a transistor radio, what would happen is this would be connected off to your car aerial or whatever else, and then you'd have your car's speaker or whatever, and then you'd have your 12-volt source. And what would happen is you'd pick up a radio signal which is coming through the air, and that would send this very, very small voltage, which you might want to amplify later on. But this very, very small signal would come in here like that, and because we're putting 12 volts out here, what would happen is the voltage we got out the other side would be a direct copy, but a much larger signal. So the old transistor radios are literally just a transistor attached to an aerial into the base, and then a much larger current which goes through. This is far, far, far too weak to drive our speaker, because the speaker needs a large enough power to push the magnet which pushes the cone. So what we do is we push a far larger voltage into our transistor, and we can amplify that weak signal significantly to drive our speaker. I mean, these are basically the two main uses of transistors are either for amplification of weak signal or as an electrical switch. Computers these days have billions or trillions of transistors which work as electrical switches because we can, when we turn them on and off, we can basically flick switches on and off, and from there we can build up logic circuits like AND gates, OR gates, so on and so forth. Yeah, so 3 terminals, base, collector, and emitter. So base, collector, and emitter. PNPs work slightly differently. They have the collector and the emitter on the other side. You don't see PNP as anywhere near as often as you see the NPN transistors. And yeah, an NPN, small signal passing from the base to the emitter. So a small voltage will pass through this way, but it basically allows a huge voltage to pass through that way. And if we have a look at... So Wikipedia's got a nice little example on NAND logic. One of these actually shows... so this actually just has those ones. I think this one shows how to build a NAND gate out of transistors. Yeah, so this is a NAND gate. So for those of you who... we just draw a little logic table. So say this is input 1, and this is input 2. We have various types of gates. So we have, and this is output. So you can imagine this is going into some sort of device, like we have 2 inputs going to some sort of device, and we have 1 output coming out. And this is basically the very fundamentals of modern computing. We have lots of things like this, these what are known as gates. We put a couple of signals in and something will happen and the signal will come out. So we can have an OR gate, and basically in an OR gate, if either of these are 1, then the output will be 1. So if this is 1, 0, 1, if this is 0, 1, 1, this is 1, 1, 1, and if they're both 0 is the only time that the output won't be 0. Everyone sort of follow that? So this is basically saying if this is 1 or this is 1, then the output will be 1, which is why it's called an OR gate. With a NAND gate, from memory, if we have input 1, input 2, and out, a NAND gate from memory is 0 and 0 is 1, 1 and 0 is 0, 0 and 1 is 0, 1 and 1 is 0, I think. Let me just double check that. And 0 and 0 is 1. Oh, sorry. Yeah. Sorry, that way. So basically, in a NAND gate, if in any situation apart from when both inputs are 1, it will be 1. Otherwise, it's 0. Now, the reason NAND gates are special. So this is a NAND gate here. And this is what it looks like. It's basically, so this semicircle here is an AND gate, and then the little 0 or here is basically means the opposite of that. So in this, the input table I just put, so A and B is 0, 0. But basically what you can actually do with a NAND gate, what makes it special is any other gate we have, we can actually build out a NAND gate. So if we want to make a NOT gate, which basically inverts the signal, we just push the same signal into both ones. If we want to build an AND gate, we can build it out of 2 NAND gates. If we want to build an OR gate, we can build it out of 3 NAND gates. If we want to do a NOR gate, we can build it out of 4. An exclusive OR, we can build it out of 4. An exclusive NOR, we can build it out of 5, and so on and so forth. But each of these are basically, you'll have millions or, yeah, probably millions of these gates in your computer to do all sorts of arithmetic and stuff like that. And you can actually build them all out of NAND. So if you can build one NAND gate, you can build an entire computer, essentially. And this example shows how you can build an AND gate. So we have 3 transistors here. So we've got 1 here, and 1 here, and 1 here. And these are our 2 inputs here, and this is our output. So if I set low and low goes to high, high and low goes to high, low and high goes to high. Sorry. But if they're both high, then it's low. So with 3 of these transistors here, so 3 of these little black boxes here with the legs, we can build ourselves a NAND gate, and with enough NAND gates we can build any other type of logic gate, which means you can build your computer processor, you can build your RAM, you can build everything else out of these transistors. Obviously, this is far above and beyond what you guys need to know again, but it's just sort of, I just wanted to highlight how important transistors are to modern computing. So you can either amplify a signal, or with it you can build a NAND gate, and from a NAND gate you can build every other sort of gate which you need to build a computer. So yeah, with enough transistors like this, you could build your own computer, and in fact people have done it, like built ridiculous, just hundreds of these guys to build a computer. Obviously these days they're using tiny, like the transistors they're using are absolutely tiny, like micrometers. But if you look at the chip diagram, it will still have millions or billions of these little transistors on it to control everything it does. And we'll take a short break there, I think. So yeah, maybe 5 minutes, and then we'll come back after that. All right, so we'll start back. Try and get through a few more slides before we finish. Taking a little bit longer than I anticipated, mainly because I keep digressing, but it's all right. Hopefully some of it's interesting to you guys. Right, so there's just one last component I want to talk about in what I consider, I guess, the components you guys are likely to run into in your projects. And then after that, it'll be a few which you might run into depending on what sort of area you work in. But yeah, the last thing I just want to talk about is relays. So we talked about switches, which are mechanical devices which make or break connections. Then we talked about transistors, which are effectively can be used as electronic switches, which make and break connections sort of using voltage. The other alternative is a relay. A relay sort of is a mix of the two. It is like a switch in that it physically makes and breaks a switch by connecting pieces of metal together. However, it is electrically controlled in that instead of you pushing a button or whatever, it uses magnets or magnetic fields to open and close a switch. So this is what a relay looks like internally. So just like switches, you can have single pull, single throw, single pull, double throw, and so on and so forth. And the diagram looks kind of the same. So we have the switch here, at least if you look at this part or this part. The difference is you also have this coil, and you drive the coil to pull on the switch magnetically. So you put a voltage into here, and it'll physically pull the switch over to close it. Yeah, so you typically use relays when you want to drive higher voltage things. So transistors are good for low voltage things. So if you want to switch on lights or like a little LED or whatever else, if you want to control things in your house, a relay is a better way to go about it, because basically you're isolating the two things. So the voltage which goes through here can obviously be, and the circuit which connects through here is obviously a completely different circuit than the one you drive. So you can imagine if you drive the coil from your Arduino, then you can wire this into the mains of your house, and you can have your Arduino flick on and off devices in your house. Just a warning, if you are controlling stuff in your house, make sure you get the right relay, because you need one which can handle mains currents. Otherwise, it is likely to, the amount of power going through it will weld that connection shut, and then you basically just have a wire rather than a relay. But yeah, you can control these things through Arduino. Typically, the amount of energy which is required to energize the coil to pull it shut will be more than an Arduino can pull, so you might need another circuit in there. Basically, your Arduino will control that, which will control the relay, which will then turn on your lamps or anything else. But now you're sort of getting into the home automation stuff, so you can imagine you might build a circuit. So when you're away from home, you're on holiday, you can have it switching on your lights and stuff, so it looks like people living in your house, you don't get burgled. Or you can do various other things. You can have home automation, so you can, connect to your Arduino or whatever from home using an Ethernet shield or a Bluetooth shield, and you can turn your TV on and off, whatever else, or your heater so that your house is warm when you get home. Just one thing to keep in mind is when basically you put a huge amount of voltage into this electromagnet here, when you turn that off and this electromagnet powers down, often you can end up with quite a huge sort of voltage spike, which can damage your electronics. So often what you have is, if you have say you have your Arduino or whatever else here, and then you have, let's just say we're running this Arduino directly into the coil, and then that goes back into ground or whatever else, and then we have our other switch here, which is connected to our mains voltage, and that's connected to a light bulb in my house so I can turn on or off. Often what will happen, you put 5 volts into here and this will charge up and pull this closed magnetically. When you turn this down, often when that electromagnetic field collapses, you'll see like if you measured the voltage across here, it'd sort of have this huge voltage spike which will damage your electronics. So often what will happen is you'll see people will put a diode backwards across the coil so that when this voltage spike happens, the voltage spike will actually go through the diode back into, because it'll be a voltage spike across the coil, and basically it'll collapse itself. So what you'll end up seeing at the Arduino will be more or less a flat line, so it won't burn it out. But yeah, I'd recommend, again, if you're doing stuff with relays, do a bit more research before you throw one in your circuit, just so you don't blow up your Arduino. And we'll have a look at a couple of devices you can use later on to isolate and protect your Arduino from things like voltage spikes and whatever else. So that sort of, yeah, we looked at some common components to begin with. That sort of ends the common components that I wanted to talk about. And now I just want to have a quick talk about some specialized components which you guys might run into depending on what your projects are or what you decide to do with your Arduinos or any other electronics you choose to use. So the first one is transformers. So this sort of just completes our little chat on building one of these things. And basically what a transformer is it uses induction, which is sort of a thing that I'm like a property of electronics and magnetism, and the relationship between electric fields and electromagnetic fields and stuff that I'm not going to go into. But basically a transformer allows you to transform the voltage and current in between devices. So what you typically have is you have a transformer core, which is some sort of iron core or something which conducts or allows for magnetic fields, electromagnetic fields to pass through it, and then you run voltage through it in one direction or through one side of it, and then you get voltage out on the other side of it. And depending on the number of what are known as windings you have on either end will depend on the relationship from it. So this is what a transformer looks like in your thing. And typically the way it works is the number of windings on one side compared to, or the ratio of windings on one side to compared to the ratio of the windings on the other side will step up or step down the voltage and the current inversely. So look at, if we look at this example, so we have, I guess, the opposite of this. So if you imagine this is the primary windings or the windings that you put voltage into, this is the secondary windings. If we had 10 here, so we wind around the coil 10, or the core 10 times here, and then on our secondary we wind around 100 times, so there's 10 times more loops around the core on this side than there are on this side. If we put 1 volt and 1 amp into this side, then we will get 10 volts and 0.1 amps out the other side. So you can see here we step up the voltage by having more windings on this side. We step up the voltage in the same way as, or the same ratio as the windings. So this is 10 to 100 or 1 to 10, and the voltage goes up 10 times, so 1 to 10 times, but the amperage comes down 10 times. So the ratio between the voltages increases 10 times, the ratio between the current decreases 10 times, because the primary to secondary windings is 10 times different. So with our transformer example before, we looked at if we put 5 volts in, or 5 volts AC in, we can get like, a certain amount. It was slightly less, it was 3.6 with all the energy inefficiencies out. But if we're doing 240 or 230 volts, we want to get 12 volts out, we might want to make that 1 to 12. So we have 12 times more windings on the primary side than on the secondary side. That will decrease the voltage from 230, 240 volts down to 12 approximately volts. And then we put our full wave rectifier after that to smooth out the current that we're getting out. Yeah, so does everyone sort of follow what they do? I'm not going to go into how they work because I don't 100% understand it myself. But basically using electromagnetic electromagnetic inductance between the two wires. You can induce a voltage in this one from a voltage passing through that, or vice versa. And the other thing which transformers can be quite useful for is isolation. So oftentimes, say you have an electric lawnmower or some sort of electric device that you plug into your house. So with you have your house wiring, you have your AC coming in, and then you have this one essentially goes to ground, which oftentimes is actually grounded into the physical earth. If you accidentally cut this wire here so it comes off, and then you're standing on the ground and you grab onto that, then you make the circuit. So you get 230 volts, and you are the load. So you get 230 volts passing across you, which is kind of less than ideal. So what we might choose to do instead is we run through an isolating transformer. And then let's say we have break our connection here. And there's me standing here on the ground. So this is an isolating transformer. So if we have, say, 100 windings, we'd have 100 windings here, which means the voltage V1 and current I1 and V2 and I2 are all going to be the same. So V1 is going to equal V2, I1 is going to equal I2. So it's exactly the same because we have the same number of windings. But what the difference now is this circuit, like with our AC current, which connects to ground, is a complete circuit. So if I break this and grab this, I'm essentially making a complete circuit. Whereas here, in order for the circuit to be complete, it has to get back around to the other winding of the transformer. So now if I have my electric lawnmower and I run over the cable and I then grab it, as long as I don't grab the other end of the winding, I won't get electrocuted. Like as long as if I'm standing on the ground holding it, it's only if this end is also connected to ground that it'll make a complete connection. So oftentimes, you know, if you have your electric sockets on the outside of your house, oftentimes they might be isolated transforming. So if you accidentally cut the wire or whatever, you won't electrocute yourself by just standing on the ground sort of thing. Of course, if you grab both ends of the wire, you're still going to get electrocuted. So I'm not using this as an opportunity to go out and stick stuff in outside sockets, but it is there sometimes to protect you. Right, so moving on, just a few other things. So light-dependent resistors and optoisolators. So light-dependent resistors work in a similar way to the potentiometers we saw earlier. So these guys here, where we have a little dial that we can turn or a sliding thing. However, they work based on light, not surprisingly. So as light goes onto these, it decreases the amount of resistance and allows a larger current through. And you can, basically detect the amount of voltage which goes through, and from that you can detect whether it's light or dark. So, you know, you have cars these days which have automatic headlights, and they'll turn on when it gets dark, and essentially they'll have some form of light-dependent resistor. So it's basically detecting how light or dark it is outside, and once the resistance of this device falls below above a certain threshold, it will go, oh, okay, there's not enough light reaching this, it's obviously nighttime, I'll turn the lights on. So you can use this for various things. Optoisolators, so these are quite cool devices, and I just mentioned them because we were talking about relays before and how you can drive stuff from your Arduino. So an optoisolator, you typically get it in a little package form like this, but it actually is a combination between an LED and a light-dependent resistor. So it's got both an LED and a light-dependent resistor in here, and you put voltage into the LED. So if you remember, LEDs don't take a lot of voltage. You put like a couple of volts through them with a resistor and they'll light up. And then you have a light-dependent resistor on the other side, which will only allow current to flow through if it's getting enough light. And so the good thing about that is if we were driving our transformer, or rather driving our relay through it. So say we have our Arduino here, and before we had that connected to our Arduino driving a relay. Oops, that should be over there. So our Arduino drives a relay, and then we forget to put in that protection diode and it shuts off and it burns out our port. The alternative we can do is we run that into what am I doing? Can't even draw an arrow anymore. Oh, actually, we need some sort of power source in here. Power source, and then just round off this one. And then connect this up like that. So now, basically, we have another power source which is driving our, or runs through our light-dependent resistor or our opto-isolator, which drives the electromagnet. But the main advantage between doing something like this is if there is a huge voltage spike here, the only place it has to go is into the light-dependent resistor, which is probably not going to do it any harm because there is actually no physical connection across here. Like your Arduino is completely isolated from all the circuits which are happening, so it's completely protected. Worst case scenario, you might burn out, this chip here, which is, like less than $1 versus burning out your $40 Arduino, simply because you've protected it by the only signal which is transferred is a little light signal which is happening internal to this chip. So, it's just a nice little thing you can use to protect your Arduino if you're driving anything which has the potential to damage your thing, so driving motors or whatever else. And it's good for interacting with microcontrollers where the input-output voltages and currents must be limited. So, if you need to drive something more powerful off your Arduino and you run 12 volts or 230 volts into your Arduino, it's going to catch on fire. Using this, there's no way for any voltage to get back across into your Arduino.
So you're saying there's a little LED in that box?
Pretty much. So there's a little LED that you can't actually see because it's enclosed in resin. A little LED and a little light-dependent resistor in there, and you turn the LED on and off, and that allows current to flow through. But because you can't conduct electricity over light, there's no chance of you frying your circuit. Right, so reed mercury switches. Reed switches are magnetic switches, so they typically look like this. You have a little glass thing with a couple of pieces of wire which sort of float in there. But when you move a magnet close to them, it pulls the two pieces of wire close together, so it's kind of like a relay. However, the magnet you typically use is mounted. So these are commonly used in home security systems. You put the magnet on the window, and then you put the reed switch on the window pane so that when the window's open, the magnet moves away, the reed switch opens, and if you turn your alarm on and the reed switch opens, you know that someone's opened the window, so to go off. Mercury switches work in a similar way, except they look like this, and they're a little enclosed glass thing with a little drop of mercury and a couple of wires on it, and mercury conducts electricity, and it's liquid at room temperature, so as this moves around, like if you tilt that up vertically, you can imagine this blob is going to float down, connect these two components together, it's going to make a circuit. So you can use these for, like you could make a car security system or something, that if somebody bangs into your car and it slops that mercury around, it's going to detect that something's happened. So if it's picked up in such a way, or if it's banged, the mercury will slosh around and set that off. Piezoelectric sensors. So piezoelectric sensors are actually pretty neat. The piezoelectric effect is the electromechanical interaction between the mechanical and electric state and crystalline materials, which basically means that certain types of crystals, if you put electricity in them, they change shape, and if you change shape, they emit electricity. So it's sort of this two-flow effect. You put electricity into them and they change shape, or you change the shape of them and they bring electricity out. So it's sort of an inverse effect. An electric charge is produced in response to mechanical stress. So if you bang on them with a hammer, they'll produce a voltage. Or if you put a voltage through them, they will move. So piezoelectric sensors can be used to detect pressure, acceleration, strain, or force by the physical forces acted on them. They'll produce a very, very, very tiny voltage. And if we put electricity back into them, we can bend them and actually use it to play music. So your old beeping speakers on a computer, like the motherboard speaker is a piezoelectric speaker, and basically all it's doing is it puts a voltage into the speaker, which has a little crystal in it, and the crystal just bends. And if you bend it at just the right frequency, it'll play a note. So you can get piezoelectric sensors which look like this, which are typically used for detecting force or whatever, and you can buy piezoelectric speakers which look like this, which you put voltage into and they play notes. So, and these slides would possibly have been a little bit used. Well, we actually talked about it earlier on, but we can play sound out of these piezo speakers or these piezo devices by vibrating objects at the right frequency. So if it moves at a certain frequency, it'll move the air at a certain frequency, the air will move into our ear and move the hairs in our ears at a certain frequency, and our brain will decode that as being a sound at a certain frequency. So in order to do that, we turn on and off the voltage going into it, and it'll cause the crystal to resonate or vibrate or bend at a certain frequency. And if we turn it on and off, we can get it to bend at the right frequency to move the air, to move our hairs in our ears, and so on and so forth. So these are basically the frequencies we like for a scale from C to high C. So if we send a frequency of 261 hertz, so we turn on and off the piezo speaker at 261 hertz, so 261 times per second, we will get a C note, or in this scale anyway, a C note. And that means we need to have a wave period of 383 or 3,830. So we're basically turning the period of the wave, so how long it lasts is 3,830 times per second. Which leads us into pulse width modulation. We already talked about this with our analog write things, but Arduinos are only capable of outputting 0 volts or 5 volts on their digital output pin. So when we do analog write, if you remember way back when, we go analog write, and then we specify 0 to 1024, was it 250? No, 255, sorry, 0 to 255, and that will give us a voltage of, whatever. But what that's actually doing is it's actually turning that switch on, 255 times a second or whatever else. So if we want to output a value between 0 to 5 volts, what we can do is we can turn the power on and off really quickly, and this is called pulse width modulation. So we can simulate an analog voltage by outputting a digital high voltage for a certain period of time and a digital low voltage, so 5 volts to 0 volts for Arduino. The entire time is called the period, and the percentage of time the voltage is high is the duty cycle. And the resulting output voltage is the average between that. So here are sort of a few examples. So this is our Arduino. We can either output 5 volts or 0 volts, but say we want to output 3.75 volts, which is 75% the value of 5 volts. What we'll do is we will turn on in our period, so however many milliseconds, we will turn on 5 volts of 75% of the time, and then we will turn it off for 75% of the time. And if we do that fast enough, the voltage averages out to look like 3.75 volts. If we wanted to get 2.5 volts, we'd turn it on for half the time, turn it off for half the time. And if we wanted to get 1 volt, we'd turn it on for 20% of the time and turn it off for 80% of the time. And if we do this fast enough, for what it looks like to the circuits, it is actually only getting 1 volt out, when in reality we're actually sending it 5 volts for 20% of our duty cycle. And this is how we do that in processing. This is how we do this on the Arduino. So if we say analog write 0, we have a 0% duty cycle, so we send out 0 volts. If we want a 25% duty cycle, we send out analog write 64, which is 1/4 of 255, which is our maximum amount, and that will turn on 5 volts for 25% of the time and then turn it off, and it will essentially give us 1/4 of 5 volts, so 1.25 volts or whatever. If we do analog write 127, we got a 50% duty cycle, so that'll average out about 2.5 volts. 191 will be a 75% duty cycle, and then 255 will be a 100% duty cycle, so it's effectively just sending out 5 volts. And we can also do the same thing to basically drive our piezo speakers and make noise, so we can use our analog write to drive a piezo speaker just as we can to imitate having a voltage. And there are examples in the processing interactivity, and the Arduino SparkFun books show you how to drive piezo speakers. I think the SparkFun kits come with piezo speakers, so you can have a play around with them. Right, just a list of a few other sensors, just to try and round this out. So thermistors work in the same way that light-dependent resistors do, except they respond to heat. So this is the thermistor here. It's usually like a little blob which is encapsulated in some sort of epoxy with a couple of wires. And as it gets warmer, the resistance decreases, and this is what it looks like. Passive infrared sensors measure infrared light radiating from objects. So you can use them, in your home security systems or whatever else, or you can use them to detect if somebody enters a room, to turn on the lights and the heating and whatever else. Ultrasonic sensors measure the distance to an object using sound waves. So one of these devices basically emits a little chirp, which is inaudible to humans, and then the other one detects when the chirp comes back. And by determining how long it takes that chirp to echo back off the object, we can figure out how far it is away. And you can buy ultrasonic sensors which fit on boards which plug directly into your Arduino, and you can get the libraries for them, and that way you can basically just say, to tell me how far away this object is. You don't need to know any of the electronics or anything which happens behind it. And these are quite commonly used by people with Arduino to detect distance. So you can do various sort of gesture-based interfaces, like people waving their hands in front of an object or whatever else. And Wikipedia has a list of sensors which is fairly exhaustive, of various things, like depending on what you want to do: acoustic, sound, vibration, automotive, transportation, chemical, electric current, blah, blah, blah. And there are just hundreds of various sensors, which you might want to do depending on what you're measuring: pressure, force, thermal heat, proximity pressure. So yeah, if you're ever wanting to sense something which is happening in the outside world, which is often what we want to do because we want to have ways to interact with our devices, have a look at this list and see what, have a look, if you want to measure something like optically detecting whether someone's there using an LED or whatever else, you can have a look through it and it'll tell you how to use these things. So there's a huge list of them that I'm not going to go into because my voice won't last long enough. So just last few sort of things, how we can interact or have our electric devices interact with the real world. So we might want to use a motor. So DC motors work with electromagnetism. So when we put electricity into certain types of device, they emit a magnetic field, and so on and so forth. So DC motors work in this sort of format. So we have our battery, which is connected to this. I can't remember if this is the rotor or the stator, but basically we have, and it's pretty hard to see, but if you look, there's actually a break in these two sides, in this thing. So power will go in through this in one direction, and then when it turns over, it'll go through it in the other direction. So it's moving through this way, and then once it goes to the other side, it'll move back through the other direction. And then we have two permanent fixed magnets in a DC motor. So one is positive, one's negative, or north and south. And so when voltage goes through one way, this basically becomes negatively charged and gets it. So here, this is negatively charged. It gets repelled from this way and gets attracted to this way. So it'll spin around here. And then once it hits that, it flicks over the other way, and now it's positively charged. And so it's going to be attracted back around here. So there's this constant push and pull of forces that spins this thing around. So you have two permanent magnets on either side, these ones here. And then we have a rotating commutator which constantly changes the magnetic field. They're simple to use. They only require a positive and negative connection, so you can literally just hook them straight up to a battery and they'll start spinning. And the speed's controlled by the voltage. The more voltage you put in there, the faster they'll turn. Unfortunately, there's no accurate way to control or measure, so they will spin as long as it takes them to spin up, and then as long as the voltage is applied, and then as long as it takes them to slow down. So if you want to drive like a car or a vehicle or something, you apply voltage and it will drive until it stops, until you take the voltage off and it stops. So there's no easy way to tell how far the thing has traveled. There's no easy way to control how far it's traveled. So if you just want to spin like a fan or something, these are perfect. But if you actually want to accurately measure them, they're not very suitable, in which case we go to stepper or servo motors. So stepper motors, like this one here, allow control of the movement of the motor in discrete steps. Sorry. So basically what we can do is, if we have a look at this thing up here, you see we have this cog in here with a bunch of teeth, and then around the outside we have these coils out here which control or go positive and negative and pull the teeth along. So we can actually control each of these by, and you see each time it sort of steps a quarter of a step. So by controlling which of these are magnetized at any point in time, so we'd go turn on, make one magnetized and it'll pull a quarter, two magnetized it'll pull it a quarter, three magnetized it'll pull a quarter, four magnetized it'll pull a quarter. We can actually control it by a quarter of a tooth rotation at a time. So we can actually control how far each of these are spinning. And typically we have a connection which looks like this. We have a common wire, and depending on which way we put voltage in, these will be either negative or positive. One way will pull it and the other way will push it a little bit. So often we'll turn one on to pull and we'll turn the last one on to push. So one will push it a little bit and the other one will pull it, and it'll just lock round onto the next connection. And we can drive it with a continual rotation, moved by a controlled angular amount, or even hold it in position using the electromagnetic field so it can't actually be turned. And we have to, basically we send these pulses out. So if each of these are ABCD coils correspond to 1, 2, 3, 4, so ABCD 1, 2, 3, 4, whatever else. If we send a voltage into here, into A, then turn that off and turn on B, and then turn it off and turn on C, and then turn on D, it'll basically go tick, 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 tick. And if you look at the end sensor, it'll sort of turn around quite jerky. If we then sort of scatter these so that they're sitting overlaid a little bit, it'll spin a little bit more freely. If we decrease the duty cycle, it'll spin more freely again. And ideally, in an ideal situation, we'll end up with turning the more as an analog sort of circuit, turning them on and off, and that'll allow the motor to spin basically freely until we want to stop it. So depending on what you want to do, you can spin it. You can turn it by a certain amount, like you could say rotate 90 degrees. You could just say spin until I stop, or you can, by turning on the magnets, you can actually get it to lock it in position, and it actually gets quite hard to turn the thing. So you basically have engine braking. And then so those are stepper motors, and servo motors are similar, but they have a reduction gearbox and a sensor, so you can turn them much more precisely, and you can actually tell how far they've turned as well. However, unlike a DC motor where we basically connect one side to one end of a battery and the other side to the other end of a battery, we need quite complicated signaling. So we saw down here how you might signal to get them to turn. And depending on how you signal it will depend on how smoothly it turns. One way we can make it a little bit easier to control motors and steppers, and in fact stop ourselves from burning out our thing, is we can use a circuit or chip known as an H-bridge. And what an H-bridge allows you to do, so this is what an H-bridge looks like, is essentially we have our motor, and then we have 4 connections on either side, which will turn the motor in various directions depending on which switches we turn on at various points in time. So it's a circuit which allows us to control a motor, and we can drive it forwards, we can drive it backwards, we can allow it to free run, so the motor will just spin down until it stops, or we can engine brake it. And I have a feeling... what is it? NeoBix electronic circuits. I think this one has... No, it doesn't. Okay. So I thought that one did have one, but apparently not. That one doesn't actually have any running examples, and that one doesn't have anything at all. That's all right. We will draw it out on paper, or on the whiteboard rather. So we have our voltage source here, and we connect it to an H-bridge. And then that goes into the motor, and then we have another couple of switches like this. And now what happens if we turn on, if this is switch 1, 2, 3, and 4, say if voltage goes in this direction, it turns the motor this way, and a voltage goes in that direction. It turns the motor that way, and we'll say that this is forwards and this is backwards. So if I turn on switch 1 and 4, electricity is going to come up here, go through the motor this way, and then go out. So if 1 and 4 are on, it goes forwards. If we now turn on 2 and 3, electricity will come through this way and go back that way and through there. So if 2 and 3 are turned on, the motor will spin backwards. If all of them are disconnected, like this, then the motor will just keep spinning, doing whatever it's doing. If we turn on, say, 2 and 4, like this, or 1 and 3, basically as the motor's spinning, it'll create a little bit of voltage which will resist against itself. So if we turn on 1 and 3 or 2 and 4, the engine will brake. So we can actually stop it using engine braking quite quickly. And yeah, so if we turn these two on, it'll go one direction. If we turn these two on, it'll go the other direction. If we turn these two on, it'll brake. If we turn these two on, it'll brake. And if we leave everything disconnected, it'll just spin freely. So we can actually control it with a fair amount of precision. And this is what an H-bridge looks like here. So it's this little chip, and chip 1 turns on the chip basically. Then you provide voltage and current, and then you apply some logic, so turning on and off various the switches. So you see here there's 1, 2, 3, and 4 correspond to 1, 2, 3, and 4. And yeah, so one's input and the other's output, and you pass in your voltage and the motor power supply. And another good thing, which I didn't mention about H-bridges, is so the IC requires 5 volts, and your logic pins have to be a certain, I think, 0 to 5 volts. However, the motor power supply can go up to like 12 or 24 volts. So, you can imagine Arduinos deal with 0 or 5 volts. So 0 or 5 volts will allow us to control the H-bridge. But say we want to drive a 12 volt motor off it, we could use the H-bridge to drive the 12 volt motor, because it has a separate power supply for the motor. So it basically, the Arduino drives the H-bridge, and then the 12 volts drives the motor. So we can actually drive higher power motors and stuff than our Arduino is actually capable of supporting with an H-bridge. And it looks after things like voltage spikes and all that sort of stuff. So it's a nice little, if you want to do anything with motors, have a look at H-bridges. They are nowhere near as complicated as they look. And of course you can build them by hand as well. But these little ICs, they're a couple of dollars and will drive a motor each. And then the last thing I just want to talk about today is, so we looked at steppers, servos, and DC motors, which all deal with rotational energy or rotational motion. Solenoids are the other alternative if you want to do linear motion, so you want something to move in and out. And basically, so motors convert electrical energy into rotational, solenoids convert energy into linear motion. So basically the way that works is we have a bar magnet which sits inside a coil, and when we put voltage inside that coil, exactly like our relays or our transformers or anything else, that becomes magnetized. And if we put the voltage in one way, it'll push the coil out. If we put it in the other way, it'll pull the coil in. So you can do stuff with pushing and pulling devices rather than spinning them. And you can buy, like I've done stuff with electric locks you have in cars, use solenoids, and basically they have a little magnet which gets powered, and it'll push, and that pushes the lock closed, and then the voltage goes through the other way, and it'll pull the lock open, so that way you can have electric central locking in your car. And I will leave that for our next lecture, which I believe Gun's actually taking your lecture on Wednesday, and so I'll have you guys on Thursday instead. So I'm pretty sure the lectures are exactly the same times, except I'll be on Thursday and Gun will be on Wednesday, because Gun is also teaching for Mark on Thursday and the lecture times clash or something. But yeah, so nothing changes. You just have me on Thursday and Gun on Wednesday rather than the other way around. Otherwise, yeah, we'll lock off there, and on Thursday we'll just finish off with some communication methods for electronics, and then we'll probably start looking at open frameworks. Does anyone have any questions, or?
So Thursday lecture time will be 8 to
What time is it normally?
4. Last time it was
Okay. I mean, to be honest, I'm happy to give the lectures whenever you guys are happy to have them. It doesn't, as long as it doesn't conflict with a meeting, I don't really care what time we have them. So
Thursday from
yeah. So what would you guys prefer? I mean, we could do 9 to 11. We could do 1 till 3. We could do 3 till 5. I don't really mind.
Understood.
What's that?
Understood.
Okay, so you're working now. I mean, we could do it from 9 if you guys wanted till 11, and that way you can still make the AR class, and we'll be finished before lunch. So it's up to you. Is 9 too early?
Just getting this discussion.
Yeah, I mean, alternately we can move it. Well, probably not Friday, but well, we could do Friday afternoon or whatever. Like I have a meeting at 11 or